Okay,
Yeah.
thank you very much. So what I would like to talk about today is on the geometry of the Hilbert space that have been overlooked for a long time. So basically everything in my talk today boils down to one equation, namely the Schrodinger's equation that we're all familiar with. And this equation, for most of us, I guess, is just a differential equation. And solve the equation, get the physics out, and we're done. But if you stare at this equation for long enough, you'll find that there are actually something really interesting, some geometrical meaning hidden inside of this equation here. And that is what we're going to talk about today. But before we talk about the geometry of Schrodinger's equation and the Hilbert space, let's talk about what Schrodinger's equation can tell us. So basically, Schrodinger's equation can tell us about the structure of the hydrogen atom. It tells us that we can have string theories. It tells us that we might have some quantum technology in the near future. But it also tells us that there are something, no matter how hard you try, it is just important to do, and those are the no-goes. And the theorems that proves these no-goes are called the NoGo Theorems, and some NoGo Theorems are listed here. Today, we're going to focus on one of the no-go theorems, which is called the no signaling theorems or no communication theorems. I'm going to focus on this theorem for two reasons. For the first reason is because it's easier to explain, and second, it has some significant impact on our understanding on entanglement states. So basically, it tells us that the communication through entanglement state alone is impossible. So let me explain what this theory is. So no signaling theorem is like this. Now assume that we have two spin 1/2 particles, and they can be spin up or spin down. But once they're entangled, for example, a singlet state, then one of them being spin up, the other has to be spin down. So you measure one of them, for example, the first part, and then you get spin up, then the other side has to collapse to spin down. And our question is, well, since entanglement state doesn't know distance at all, so we can move these two particles far, far away. And using this, can we use the entanglement as a protocol to set a communication, send a signal to a faraway distance? And it turns out you cannot. And the reason is the following. Here's a quick observation. For simplicity, we call one particle particle 1, the other particle 2. So if we try to figure if we can measure, we can send a signal from particle 1 to particle 2 through entanglement state, we have to make a measurement, right? So let's see, what if we make the measurement on the first particle? Particle 1 first. So if we measure this particle, there's a chance that you get spin up. And according to this state, we know that particle 2 actually collapsed to spin down 50% of the time. And if you measure spin down, then the other side collapsed to spin up, also 50% of the time. But what if particle 1 hasn't been measured at all? We measure particle 2 first. Then you'll get 50% spin down and another 50% spin up. So if you look only at particle 2, you actually can't tell the differences because they're exactly the same. And this is not specifically for this state. You can choose any arbitrary state and you find that their probability of getting spin down and spin up, no matter the first particle has been measured or not, they're all the same. There are no differences. So that you cannot send a message through entanglement state alone. That means, well, you cannot have a superluminal communication, because if we can send a message through that entanglement state, then we might be able to have a superluminal communication. But now we say, well, it's just impossible. But if you want to prove this rigorously, then we have to go back to the Schrodinger's equation. And we know that in standard textbooks, this Hamiltonians are said to be Hermitian. But now since we abandon this idea here, then that means we can do more things, right? So let's see what we can do on our quantum physics. So hydrogen atom is still there. String theory might still be there. and we still have quantum information, quantum technology in the future. But what about NoGo theorems? Let me rephrase what I just said. We can do more things with more Hamiltonians. That means there are less things that cannot be done. I know it's a double negative, but that's the case. So actually, we have to go back and check the NoGo theorems, because those are the theorems that tell us something that just cannot be done. And in 2014, actually a group of people, they found a non-Hermitian PT-symmetric system violates the no signaling principle. And inspired by this paper, this study, a lot of people went back and checked a lot of NoGo theorems, and they found that many NoGo theorems are actually violated in non-Hermitian regime. So our community splits into three parts. Some people, they believe that NoGo theorems, those NoGo theorems, they should be correct because they are the foundations of some physical laws. But some people, they believe in non-Hermitian physics, so they believe that these NoGo theorems can be violated. But there are still some people like me, we believe that there is a missing link between these NoGo theorems and the non-Hermitian non-Hermitian systems. And so we go hunt for this missing link. And here's what we found. We found that actually geometry of the Hilbert space plays an important role here. Let me show you why geometry matters. Here is a two-dimensional surface, and there are 2 points on this surface. What is the shortest path between these 2 points? We would say it's a straight line. A straight line goes between these 2 points is the shortest. But that's actually not true because I haven't specified what kind of geometry we're in. Maybe we're on a sphere. These 2 points are on a sphere, and we want to make sure that every single thing, every single path is they stay on this sphere. And if you have a straight line goes into between these 2 points, then that is going into the sphere. That means we're out of, it's not on the sphere. We want to find the shortest distance that's on the sphere, which is the geodesic. But how do we take that into consideration? So let's look at the inner product of the Euclidean plane. So we have 2 vectors, u and v. We make an inner product, it's just u1 v1 plus u2 v2. And you can write it simply in a simpler form, the metric, column matrix, u and v. So you just take the u transpose acting on v, and that is the exact same thing. But for non-Euclidean spaces, well, there are more things we have to take into consideration. So for example, the cross terms, we now have the cross terms. We have u2 v1, u1 v2, and also we have some coefficients here. Those are called a metric, or in our Hilbert space example, it's a fiber metric. But no matter what, there are some proportional constants here. And this can also be written in a very simple form. Looks like this. So still u1 transpose and v, but you have to squeeze a metric g in between u and v. And this is specifically for non-Euclidean spaces. If you take this g to be 1, then it goes back to Euclidean space. So this is very general. And let's look at the similarity between this inner product and this inner product of our quantum states, which is just replacing this t with a dagger. The Hermitian conjugate of u acting on v, that is our inner product in quantum space. So we're thinking, hey, can we sort of generalize this to our quantum states? And that's our proposal. And what we found is, okay, now we can generalize this Euclidean Hilbert space to a non-Euclidean space by just squeezing in a G metric, a metric, an operator, squeeze it in between the browsing and the cats. But this is not the end of the story, because we have to find some constraints on this G. And the first few constraints that we found is that we want to make sure that this inner product still gives us this Hilbert space back. So let's look at the property of Hilbert space. Well, In Hilbert space, when you switch the bras and the cats, switch the role of bras and cats, you get a complex conjugation. And also the inner product of itself is greater or zero, is greater or equal to zero. And that translated to G, it tells us that G has to be Hermitian, and it's a positive definite operator. But still, this is too broad. And this is just mathematics. We want to find some physical condition to even constrain more on this G. So we can find a more physical G for the Hilbert spaces. So we already know that it comes from differential geometry. So let's borrow something from fiber bundle, which is part of differential geometry, and apply it here. So where do we borrow it? Parallel transport. So if I want to parallel transport this vector, the blue vector, along this orange line, from this point to the other end of the orange line, it's very simple, intuitive. You just parallel transport it as the way you thought. And then we transport it along this, the other orange line to the other end and transport it back, and you get the original vector. And at every single point, it's a parallel transport. But it's very different when you're on a sphere. So we have a blue vector, it's on a sphere, and we want to parallel transport this vector along this big triangle here. So let's take a look what it would look like when you transport it along this theta direction. So when you go from North Pole to the equator, then what you find is, well, if you're sitting on the sphere, you don't feel anything different because the direction is still the same, remains the same. But when you pull yourself out of this sphere, you'll find that, hey, the vector seems to change its direction. But nevertheless, let's keep transport it along the equator and then transport it back to the North Pole. And you'll find that even the vector itself changes its direction, although at every single point, we're parallel transporting this vector. And how do we describe this phenomenon mathematically? So assuming that this vector is called V, so it has two components, V theta and V phi, and the parallel transport along this theta direction is that nabla theta on V is equal to 0, where this nabla theta on V is partial theta plus some matrix acting on V. And also, if you parallel transport it along this phi direction, then it's just nabla phi on V is equal to 0. And this actually gives almost the same form, the partial phi plus some matrix acting on V. This is called a covariant derivative or a connection, if you will. And if we can define a similar operator on the quantum state, so we define this nabla T acting on a quantum state, which is equal to partial T plus IH. Now this looks familiar. This has to equal to 0 because this is exactly the Schrodinger's equation, but it also looks like a parallel transport. If it walks like a dog, it screams like a dog, it quacks like a dog. Why don't we call it a duck, right? So we call this thing a connection or a covariant derivative. Now we have more geometrical meaning to this Schrodinger's equation, and we can use this connection to find a connection compatible metric. That is, this nabla T acting on the inner product has to equal to 0, and that sets a constraint, a physical constraint on this G. But still, this is, excuse me?
What was the capital gamma in last slide?
Oh, it's a metric. It's a matrix. This gamma, right?
Okay. Thanks.
You're welcome. So now this is mathematics. How do we show that it actually has some physical meaning? We went back and see these NoGo theorems. So these NoGo theorems hold in Hermitian cases, but they were violated in non-Hermitian regime. But we can show that it actually works in non-Hermitian regime if we take this G into consideration. So let's assume that this green thing is a Hilbert space, just an illustration. So I'm not going to show the whole proof, but let me show the most pivotal part. Okay, so in Hermitian cases, well, when we have two vectors, they were initially orthogonal with each other, then they're always going to be orthogonal with each other. But that's not the case in non-Hermitian case. So we have two vectors, they were orthogonal with each other initially, but as time goes, maybe some of the vectors wiggles. So that means they're not always going to be orthogonal with each other. But when we take this G into account, so we take the new inner product that includes the G, so we take the geometry of the Hilbert space into account, then when they're initially orthogonal with each other, then they're, when the phi is wiggling, the Hilbert space is also wiggling with it. So that means they're always going to be orthogonal with each other. So that completes the proof. So we show that although we first thought they're violated in a non-Hermitian regime, but they're actually they actually are right. They're still right in non-Hermitian regime. So we take this further and we try to calculate a lot of geometries of some Hamiltonians, assuming that this Hamiltonian has a depends on the parameter gamma. And we can dial this gamma to some other values. For example, here, then we get different geometries using this equation. But there are some special values, some critical values. When you dial it across this value, then the many properties would change. Physical or geometrical property can change. So let me take an example here. This is one of the often seen property that has been changed. When you dial it across this critical value, gamma GPT, your the Hilbert space becomes time dependent. And when you dial it down, when it passes through this critical value, it becomes time independent again. So this is very interesting. It looks like a phase transition to me, but I'm not an expert on this. So I went seek for help on my condensed matter colleagues, and they told me that there's something that they use to detect phase transition in condensed matter, which is comparing the ground state between two different Hamiltonians, nearby Hamiltonians. So now we define something called fidelity. It's a quantity that defines the similarity between two states. And now we use this to find the similarity between the ground states of two Hamiltonians. So for example, this side gamma is the ground state of H gamma, and the other one is the ground state of H gamma plus epsilon. And then use this, if you expand it around epsilon equals 0, then you get the next two leading order term is epsilon squared term. And we call this thing fidelity susceptibility. And these people, they use fidelity susceptibility to detect phase transition because it blows up when it reaches the critical value of phase transition. And now we have more things. We know that the geometry actually plays a role. So we generalize this fidelity to include this geometry by adding in this G, the metric. But what about the ground state fidelity? There's a difficult part of finding this fidelity because one of them is the ground state of H gamma. The other is the ground state of H gamma plus epsilon. That means we have two geometries here. So they might look similar, but they are still different. So what do? We just we actually take the geometry seriously, so we can generalize this as the following. This G always goes with the bra, so that makes the bra vector the double angle bracket. The double angle bra is exactly the dual state of the cat. So we use this and we find that it's, if you expand it around epsilon equals 0, then we find its next leading term is still epsilon squared, and we call it the generalized fidelity susceptibility. And we find that it actually blows down to negative infinity when it reaches gamma GPT. So let me just show you one really simple example, an SSH model. So now it blows up at the phase transition point, but when you add in some non-Hermitian terms, it blows down to infinity at 2 points. And we found that actually it's the boundary between three different phases. So it's actually very similar to phase transition. So to wrap up my talk today, is that we found a geometrical realization of the Schrodinger's equation, and then we used that to find the geometry of the Hilbert spaces, and then we used the geometry of the Hilbert space to generalize this fidelity, and then we find a phase transition-like phenomena using this fidelity. And that'll be the end of my talk. Thank you very much.
Yeah, thank you, Ju, for your nice talk. We have time for a couple of questions. Yeah, go ahead.
Yeah, hi. When you generalize the fidelity to the case with the metric,
Yes.
you seem to be comparing vectors in two different Hilbert spaces. Don't you need to like parallel transport across the fiber bundle or so?
Yeah, actually, that's part I don't really understand as well, because yeah, I guess you're right. So we should take the lead bracket instead, I suppose. Is that your question?
Yeah.
Yeah, that part I haven't really figured that out, but
Because you're taking overlap of two vectors in 2 points in the bundle, so it
yes.
doesn't look it should make sense. Yes.
Yeah, yes, because we're just generalizing the original fidelity to whatever, just by taking the geometry into account, but we didn't, like we haven't really have full understanding of this thing yet.
Okay, thank you.
May I have a question?
Yeah,
Yes,
please.
In this notation, there is something which is very well compatible with my own talk, where I use different notation. But the point is that if you have this change of gamma parameter,
Yes.
and which implies a change of Hilbert space. So if you have systems which are not open, I mean, if you just study it as fundamental theory, so this means that you start from Hamiltonian, which is given, which is non-Hermitian, but which is due to geometry compatible with standard quantum mechanics. But this reconstruction of the space is ambiguous. So could you have a comment on this ambiguity of reconstruction of the space for a given Hamiltonian, which means if you have two observables, that's something which is a difficult question.
I'm not sure if I understand the question right. You mean like we can compare the observables in different Hilbert spaces? Is that your question?
Yeah, that's one of the basic things which is with this PT symmetry theory, because if you have PT symmetry theory, so you have this what's called charge. If you have charge, yes. So it reconstructs your geometry. Yes. It is your G. I mean, you get your metric in yes. Hilbert space, in a product metric. Yes. But this reconstruction from given Hamiltonian is ambiguous. It is not unique reconstruction. And the choice of charge is one of possibilities. So if you make different choice, so you have different Hilbert space, and what you need is complete information, which means that you need not only Hamiltonian, but also another observable to be able to make it unique.
Well, because I'm thinking this in terms of gauge theory. So in gauge theory, you can have any arbitrary gauge choices, but they all turns out to have the same physics. So I'm guessing, I'm not sure about how the observables transform from one to another. Actually, in our paper, we actually show that there is a way of transforming it, but how exactly do you define, there's no unique way of defining those matrices as well.
Maybe we could establish email connection and clarify things. They are not easy to, I mean, I shall send you email.
Okay, yeah, sure. Thank you very much.
Yeah, one last question from Jacob. Can you go ahead and ask the question?
Oh, hello.
Hi.
I had seen a paper of yours regarding the NoGo theorems for your non-Hermitian physics. In advance of the talk, I was spoiled. So I had a question. For a couple of the proofs, I think there's some implicit assumption that the metric operator you use factorizes as a tensor product with the Hilbert space.
Yes.
Have you checked what happens in the case where that's not true, where the metric operator has a non-trivial Schmidt decomposition?
Actually, no. And
okay.
that is very that is harder than I originally thought. So yeah, you're right.
Okay. I'd be more than happy to talk with you about this, say, over email.
Oh yeah, sure. Thank you very much.
Thank you.
Okay, so let's thank Ju for his talk.